Good morning, students. Our next theorem based on singularity is a function which has no singularity in the finite part of the complex plane or at z is equal to infinity. Such a function is constant function. So let us take the function f of z. Either this function has no singularity in the finite part of complex plane or this function has no singularity at z is equal to infinity. So if the function has no singularity in the finite part of complex plane, then we can expand this function about the point z is equal to 0 by using Taylor's theorem. So we can write f of z is equal to summation an z raised to the power n, where n varies from 0 to infinity. Here this z is a point inside or on the circle z mod is equal to r. Here r is arbitrary large positive number. In the second case, if the function has no singularity at z is equal to infinity, then the function f of 1 by z, that is analytic function at z is equal to 0. So we can expand it by using Taylor's theorem. So its expansion can be written as f of 1 by z is equal to summation bn z raised to the power n. Here n varies from 0 to infinity. Now from here we can obtain f of z by replacing 1 upon z by its reciprocal. So from here f of z will be given by summation n varies from 0 to infinity bn into z raised to the power minus n. Now we can compare the equations 1 and equation 3. If we compare the two equations from here, on comparing we get a naught is equal to b naught and a1, a2, a3 up all the terms, and also b1, b2, b3 all bn, they are 0. So we can write f of z by putting the values in the equation 1 again. So from there, because only a naught is left and all the other values are 0, so f of z is equal to a naught. So we get the function f of z, that is a constant function. So this completes the proof of the theorem that if a function has no singularity in the finite part of complex plane or at z is equal to infinity, then the function is constant function. Now in the next theorem we show that a function which has no singularity in the finite part of the complex plane and has a pole of order n at infinity, such function is a polynomial of degree n. So let us take a function f of z which has no singularity in the finite part of complex plane. So we can expand it by using Taylor's theorem about the point z is equal to 0. Its expansion is given by f of z is equal to summation an z raised to the power n, where n varies from 0 to infinity. Now because the function has pole of order n at infinity, and therefore f of 1 by z will have pole of order n at z is equal to 0. It means the principal part of the Lorentz expansion of this function will contain n terms, and therefore the Lorentz expansion of the function can be written as f of 1 by z is equal to f of z plus summation m varies from 1 to n bm z raised to the power minus m. This is the principal part which contains n terms. Now again from the equation 1 we can obtain the value of f of 1 by z by changing z into 1 by z. So the right side becomes summation n varies from 0 to infinity an z raised to the power minus n. Now we can compare these two equations. If we compare these two equations, we get f of z plus summation bn z raised to the power minus m is equal to summation an z raised to the power minus n. Here n varies from 0 to infinity. On the left side m varies from 1 to n. Let us simplify this equation. This can further be written as f of z plus b1 by z plus b2 by z square and so on. The last term will be bn divided by z raised to the power n. On the right side, this series will become a naught plus a1 by z plus a2 by z square and so on. So from here, comparing, we get f of z is equal to a naught, b1 is equal to a1, b2 is equal to a2 and so on. Bn is equal to an, and an plus 1, an plus 2, all the other such terms, they are 0. Substituting these values in the equation 1, we get f of z is equal to a naught plus a1z plus a2z square and so on. Last term is an z raised to the power n. So this shows that the function is a polynomial of degree n. So this completes the proof of the theorem. In the next theorem, we show that a polynomial of degree n has no singularity in the finite part of the complex plane, but has a pole of order n at infinity. So let us consider a polynomial of degree n given by pz. This is a naught plus a1z plus a2z square and so on, an z raised to the power n. Here an is not equal to 0 because the degree of the polynomial is n. From here we can find p of 1 by z. That will become a naught plus a1 by z plus a2 by z square and so on. The last term will be an upon z raised to the power n. Now we can see that this has a pole of order n at z is equal to 0. So the function p of z, that will have pole of order n at z is equal to infinity, and also this polynomial has no singularity in the finite part of the complex plane. Now our next theorem is based on essential singularity. This theorem is the Asterisk Theorem, which states that if z is equal to z naught is an essential singularity of the function f of z, then given positive numbers epsilon and r and any positive number c, there is a point in the circle with center z dot and radius r at which the mod of f of z minus c is less than epsilon. It means in every arbitrary neighborhood of an essential singularity, there exists a point at which the function differs as little as we please from any pre-assigned number. In order to prove this, we use contradiction method. Let us suppose the theorem is false. Therefore, for given epsilon and r greater than 0 and a number c, there will exist a point z naught in the circle with center z naught, radius r, at which the absolute difference of f of z with c will be greater than epsilon. Taking reciprocals from here, we get 1 upon mod of f of z minus c, that is less than 1 by epsilon, and therefore we can say that this function has removable singularity. It means the principal part of Lorentz expansion will contain no term, and therefore we can write the expansion of this function, which can be written as 1 upon f of z minus c is equal to summation an z minus z naught whole raised to the power n. Here n varies from 0 to infinity. We can expand this summation. This can be written as a naught plus a1 into z minus z naught plus a2 into z minus z naught whole square and so on. Now we have to show that a naught is 0. If we take a naught is not equal to 0, then from here taking z is equal to z naught, all the other terms will 0. The right hand side will become a naught and the left hand side will become 1 upon f of z naught minus c. Taking reciprocals, f of z naught minus c is equal to 1 upon a naught. From here the value of f of z naught, that will be c plus 1 upon a naught. So this shows that the function 1 upon f of z minus c, this is analytic and non-zero function at the point z naught. And because this function is analytic, therefore the function f of z, that is also analytic at z naught. But this is a contradiction to our assumption, because the point z naught is an essential singularity. Therefore, if we take a naught not equal to 0, we get a contradiction to given hypothesis. Therefore, a naught must be 0. Now, if an is 0 for n is equal to 0, 1, 2, 3 and so on up to m minus 1, and am is non-zero, then the equation 1 becomes 1 upon f of z minus c is equal to summation n varies from m to infinity an z minus z naught whole raised to the power n. Now this can further be written as am into z minus z naught whole raised to the power m plus am plus 1 into z minus z naught whole raised to the power m plus 1 and so on. Now let us take z minus z naught whole raised to the power m common. Inside we are left with am plus m plus 1 into z minus z naught and so on. And this is the definition of 0 of order m. So we have shown that the function 1 upon f of z minus c has a 0 of order m at z naught, and therefore its reciprocal function will have pole of order m at z naught, and also c is constant. Therefore the function f of z has pole of order m at z naught. But this is contradiction. This contradiction proves that our assumption is wrong. It means absolute difference of f of z with c will be less than epsilon. So this completes the proof of Asterisk theorem.